this works. Good. Start.
So now we have Christian Copetti from Oxford, who will tell us about non-invertible symmetries and anomalies and how they can be used for understanding scattering amplitudes.
Okay, yeah, thanks a lot for the invitation. So I have to apologize because I have other slides for this talk, but they got lost. I was walking in Iceland and they were on my phone and the phone broke. Turns out volcanic ash is not very good for your phone. So I kind of had to recycle this a bit. Okay, just because there would be some parts which are not right. Okay, so let's situate. So I have to this disclaimer. So let's situate the talk a bit. It's a bit of a multidisciplinary thing. So there are three things. One is generalized symmetries. We'll talk about how they constrain scattering amplitudes. And we'll have some integrable examples, just because we don't know S-matrices exactly for non-integrable systems, and we wanted to check. But the methods are general. And so let's go. In summary, I will tell you how categorical symmetries, generalized symmetries in 1+1D for this talk act on massive kinks. So we'll just study RG flows that start from some CFT and go to some gap theory. So we don't study the integrable flows between CFTs, for example, but one probably can generalize this to this case. And what are the world identities for S matrices? In this case, I do 2-2-2 case. You can derive them in any case. It's very similar. And this is kind of the picture. You have a topological line, which is red, and this is matrix, and you want to pass it through and say what's happening. So what we'll see as a first result, which is it appeared in March this year, is that if impose symmetry, which will be this identity I will tell you about, unitarity for the S matrix, and also the Yang-Baxter equation, because we're going to do integrable samples. This you can also not impose, but the example will impose it. And then we will see that this is in tension with the standard crossing symmetry of the S matrix. And actually, the crossing symmetry will be modified in this manner, where this dA, dB, dCd are quantum dimension of some lines. I will tell you how they come out. And they probe the symmetry breaking structure in the infrared. Okay? So, and this will correct some mistakes in the integrability literature, so we'll tell you what you have to change. And okay, this is what I didn't have to put. Okay, so what is the philosophy of how I think about this program? So it's the other way around. You start from the IR and you try to build a theory in the UV. So the first thing you see in the IR is gapped vacua, because it's just a massive theory, but it's symmetric. There is some symmetry, so it's not just gapped vacua, it's a symmetric TPFT, called M. If you go a bit above in energy scale, you go to the mass scale of the kinks, so you will see kinks K and B interpolating between the vacua. This is what I will describe. But if you have this, in the integrable case, you can also, if you have the S matrix, you can do a TBA, so you can actually probe the UV, which is a UV CFT perturbed by some relevant operator. In that case, some work in progress is to find out new conformal data starting from the S matrix for symmetric theory. Okay, and just let you know that the symmetry is presented all steps. So in the IR it acts on the vacua, it acts on the kinks, which I will explain how it acts, and then it's the symmetry which is preserved by the relevant deformation in the UV. Okay. So I think this I can kind of skip a bit, just fast review of fusion category. So this is just topological lines in 1+1 dimensions. They have some fusion structure, and they have some associativity conditions. We will not enter in the talk, so just keep in mind that there is some mathematical structure below. And we'll need just the quantum dimension, which are the valve on the circle of the lines. Just an example, usual example is the Ising symmetry. So you can consider the 1+1 dimensionalizing the phase diagram, and Reynolds one-year duality which exchanges at low temperature. And then at the critical point, this becomes a symmetry. So you don't have only the Z2 of Ising, but a new generator which is called the N. And this is the symmetry, which is maybe the most well-known one. You have seen REPES3 as another example. And the quantum dimensions are these ones. There is some non-invertible symmetry. Okay, so let me just describe QFTs very fast. So I will use this reference. This is also the work by Laksha and Lea and Sakura and company, which use the symmetry TFT, but just for the sake of convenience. You can think of 1 plus 1 dimensional TFT, which is symmetric, as a collection of boundary conditions, which I call ABC, as the ABC in the modified crossing, and topological junction with symmetry lines, which are these, which also satisfy some associativity conditions. These ones, there's some C-valued symbols that enter, and there is some fusion of the line with the boundary condition, which gives some matrix algebra. It's called the NIM matrix algebra, and this gives the structure of a module category over C to the set of boundary conditions. It's just a mathematical name to tell you how the symmetry acts on these discrete boundary conditions. Okay, and the Ising example, for Z2 there are two TQFTs, Z2 is potentially broken or not, and these are exchanged by the Kramer-Zweiner duality, and this is the action on the vapor, the only one which is consistent with the integer nature of this NIM representation. And you can check that lower vapor are inconsistent with this NIM representation. Right. And this is the special case of something which is called the regular representation, which is like the adjoint representation in some sense. It's always there, it's the biggest representation that you have. And it's just, and you just identify the vapor with a set of lines. So that's just something that's always there. And the structure of module category is just the structure of the category itself. And physically it just means that the symmetry is spontaneously broken, but in a maximal manner, so it has a physical meaning. And we will just see this essentially in most of the talk. So just keep this in mind. So let me also talk about the kinks. So this is how the symmetry acts on TQFT. Now we have the kinks. So how does symmetry act on kinks? So first there is this very nice idea in this paper that you can think of the kink Hilbert space as a strip Hilbert space with very large length and boundary condition at two sides, which will be just the boundary condition defining the TQFT vapor because of that very low energy. And the excitations here are kinks which interpolate between the two sides. Now this is kind of obvious. And there is also a nice symmetry TFT description of this, which appeared in a paper by me, Shota, and Lucia, and by Clay, Cantaro, and Olfester some weeks ago, a couple of weeks ago. But and the symmetry action is just taking a line, you put it horizontally, and you make it act downwards. Downwards are the states. Okay, it has some matrices, and it has some consistency condition. Just changing it gives some very complicated algebra. It's not very interesting, but there is a way to find what are the irreps of the algebra. So an irrep of the algebra is a multiplet of kinks, which all have the same mass, and are exchanged by the symmetry. And the prescription, I just give the prescription, like the motivation was in the other slides, so but you can ask me, it's easy to explain. It turns out that irreducible representation of this algebra are labeled by lines in this C2LM category, which Lea also introduced, which she called rho, I call V. Right? That's the same thing. So if I give you one V, I define one multiplet of kinks. Okay? So I can just label the various V's, and I tell you what are the possible kinks, and the symmetry acts in a closed way on them. Okay, and well, this I don't need, but importantly, these V's are lines, so they have their own fusion algebra. You can put them together, and this gives you selection rules on possible bound states. So this is very important for scattering amplitudes because it will tell you that some poles cannot appear in the S matrix. There is some channels of the S matrix, and this is not obvious if you don't have this machinery. If you don't know about the symmetry, you will not know that you need to look at this kind of stuff. So let's do the simplest example, which is tricriticalizing CFT M54 to the M43 in this notation with 513 deformation. This is very well known, it's very old integrable flow. If you put the sign right, you go to Trivacqua. It's known by essentially by Zamolodchikov, and these Trivacqua have an Ising symmetry. When the Trivacqua are just the ones introduced before, and you can look at what is. It's known that there is a kink which interpolates between this vacua, and described also by Zamolodchikov, and you can understand which one is the multiplet of the kink, and this is labeled by the line n in the C dual M, which is in this case just the same. This is the kink multiplet. And then in the literature there is this following S matrix with this green factor on top. And this, the Z is a CD factor, we don't care about it, okay? And the rest is the structure of the vacua. And the green factor, you have to put it to enforce crossing symmetry, otherwise it's not crossing symmetry. But what we'll see now is that this is incompatible with the non-invertible symmetry, the rising symmetry. This is Zamologikov didn't impose, but it's like a fundamental statement that you have to make. And then you don't have, you cannot do this part. And so the way to describe world identities is to start from a Euclidean disk with 4 insertions of boundary changing operators and do an analytic continuation for large disk. Kind of in picture is this. And then you ask about what is the symmetry action boundary condition, which I told you about, and on the line 3. And this is kind of the slicing you have to do. Continuation. And then a world identity, you just insert the line like this on the disk, the form up, the form down, and you find some relation, which is this ugly formula here. And these LVs are just the matrix of the representation of this symmetry answers. You know them, you input them, and you have to satisfy this. And this is one example of below of the one for rising. And okay, so you can check if you try to impose this to the Zamologikov one, it doesn't work. Take it out. And there's also a way to prove this modified crossing by analyzing the norm of the states for this disk partition function and normalizing the states properly. I will not go through this because I don't have the time. But you can show that this becomes the right crossing relation, well, these are norms of states, and gives us the modified crossing equation. So then we believe this is some fundamental thing that is a consequence of the spontaneously broken symmetry. And this is just the formula you get in this case by evaluating. And I just wanted to conclude by mentioning some bootstrap applications. So we wrote a paper about S-matrix bootstrap for the non-invertible symmetries. So how to input this in a different kind of program as like input and then bootstrap the possible partial amplitudes for the S-matrix. And just flash some results for the Fibonacci category. It's the simplest one. So you just impose the usual stuff, but you also impose symmetry. So when you do it, you decompose the S-matrix in some partial amplitudes, which satisfy the world identities automatically. But there is a simple way to do it, but we don't have time to review it. And this is just the results for Fibonacci, so this Fibonacci category. This is the amplitudes we bootstrap, this one, just labeled by the Fibonacci line. 0 is the identity, 1/2 is W. And this G is the residue of the pole of the bound state between the two kinks, the kink and itself, kink anti-kink. So it's a two-dimensional plot, and the loud region are in this kind of shape here, dimensional shape. And then there are some special points, which is this point here, which is integrable. This is integrable flow from M43 plus pi to 1, which is known. So this is we find again, like some memory was done. Then there is a special point also here that I didn't have in this figure at G equals 0. And you can ask what is special about G equals 0. So at G equals 0, you can match it with some deformation of pot CFT, which also preserves the filter Z2 symmetry. And the symmetry is Fibonacci times Z2, which is these 4 lines. And there is the kink in this double prime multiplet, it's just W times the eta. But W prime squared is 1 plus W. So it means that if you fuse the kink multiplet with itself, you cannot get it again. So there cannot be any resonance. And this force is G equals 0. This is a consequence of symmetry. And there are also some special points here and here, which we don't really, there is a special point here and one here, which we don't really know what theories are, but the integrable theories which have Fibonacci symmetry. So just up. We just flesh out the current future prospect. So one, I told you about this UV observables using TBA, which is something we're studying, and now I think we know to do it. But you need to find some symmetric S-matrix, and then you can infer things about the UV conformal data, and especially the structure of the theory in the twisted sectors, which should be sensible to the modified crossing that we've described. And another very nice example to do is this Agerup symmetry, which people have tried to construct CFT, which is with this algorithm symmetry for a while, and they have some kind of lattice extrapolation that tells that this exists, but just numerics, and the TBA is very, very precise, so it will be very interesting to use this. And what I like more probably is just application to higher dimensions. So there are two avenues. One is 3D. There have been some results by Wallace group 2 years ago about crossing symmetry in Chern-Simons matter theory and its modification. So it would be nice to give like a very concise derivation of that and understand what is the fundamental thing driving it. And another very nice thing is either monopole scattering in 4D, which has been studied recently too. And I also like maybe to study the confining string or other extended defects, which interplay with one-floor symmetry in a nice way. This would maybe give some insights in strongly coupled regime of confining H theories, which otherwise don't have. So I would there's nothing as fast. Right? Okay, thanks.
So I have a question about your last slide. So in the last slide, in the second last point, you talk about this paper.
This one? Or is
this one.
Okay.
Yeah, so in the second last point, the second last point that has some text in it. So, there you talk about this paper by Van Bees, Boyle, and Tong. So actually we were talking about this paper some months ago, by we, I mean me and my advisor. So this thing, do you think that there are some relations of this thing with Hanani-Witten effect? Because it also, well, how should I put it? Because the scenario that they are considering, it looks like, the scenario that we have in Hanani-Witten effect as well.
People have connected this non-invertible symmetry that is present here with Hanani-Witten effect for breaks already. So
okay.
This, I think Sakura's group did it. There was a paper also by Ekman company. This is kind of, yes.
Okay.
I don't know, right? This is for kind of supersymmetric stuff, but
okay, thank you.
if that's probably what you were looking for.
Sorry, I have a naive question. Do you have an intuition for why this modified crossing could be related to 't Hooft anomalies or not?
Yeah. So the point is that when you have 't Hooft anomalies, and you have this scenario when you go with the infrared two gap theory, then you have spontaneous symmetry breaking always. So then you can have distinct vacua and you can have these factors of the ADBDC in front. If you don't have 't Hooft anomaly, usually if you do the same, you're expected to go to symmetry preserving scenario with one vacuum, you don't have kinks. So, or at least there is some deformation which will drive to that. So I think that in that case it shouldn't be present, this modification. But we don't have like a definitive proof. But all these categorical symmetries that appear in the integral in 1+1D are usually anomalous because the quantum dimension must be integer, not a 't Hooft anomaly. So it's hard to find a case which is anomaly free.
Thank you.
A general question is again about the higher dimensional one. Here you discuss specifically about monopole scattering. Would you envision being implications for S matrix, or the standard S matrix of elementary particles? I mean, all symmetries, the S matrix should commute without symmetries. There should be some implications. So.
Yeah, it's just that this generalized invertible symmetries in higher dimension act in a interesting manner on extended operators. So like for particles, they act like a Z2 symmetry, something like that. So it's something that you already know in some sense. It's not a new constraint. But for extended objects like confining strings, Wilson lines, Toft lines, this kind of stuff, it's not understood what the constraints are. So that's why I want to look at that. I suspect even one-phone symmetry has some interesting interplay in the context of the confining string, but they didn't work it out yet. So for point like particles, this is what we're asking. In higher dimension, these symmetries always act as discrete symmetry, so you already know the selection rules, which are the ones you expect naively. Like you get some minus signs for the particles. So
there could still be non-linear relations. Why, if you could start inputting more issues of density, unitarity, crossing, and so on. When there's no linear link. Clearly, at the linear level, as you say, it acts in a very simple way. But if it's property of the theory, it might have.
I think that also for this modification of crossing will appear for extended operators only. So you need to look at some new thing. But it's just my intuition, so like.
Yeah, sure. Thank you.
Yeah. So at least in 4D, I'm familiar with the derivation of crossing equations from analytic continuation, and so you just derive something and you get some crossing equation, right? Are you saying that this one is incorrect, or that this makes an assumption, this derivation is an assumption that's not?
I think the problem is that you have spontaneous symmetry breaking, so you have the multiple vacua. That's what breaks down here. If you have like single vacuum, which is usually what you do in S matrix in higher dimension, you have one vacuum, you just have particles, because domain walls are extended object in higher dimension, so you don't consider the scattering of domain walls, then it's okay. Then there could be some problem if you consider scattering of domain walls in higher dimension. Okay. But the analytic structure of that is apart from those two. So you have no idea of the analytic structure of that S matrix. It's hard to say anything. Here, just particles, like domain walls are like quite flat.
So, since there are no more questions, let's thank Christian again.